Welcome to Business Calculus. I'm Greg Brubaker, your instructor for this online course. I hope that you can find this online course to be of value and somewhat interesting as you go through it. We will deal with some things that if you get into larger business settings will be helpful. If you go on to further studies for a master's, this kind of information they will assume that you already know. So this can be a valuable course for you. The first lesson or two in this business calculus course will review some lower math things just to make sure that you're up to speed and ready to go for the calculus things. First, a quick review of number lines. So if you see these in the book or other places, you're just familiar with them. When you're working with this kind of thing, remember that whenever you have an inequality, such as the first one, both of the signs is less than or equal to. When a is less than or equal to x, which is less than or equal to b, we would graph that. A is the smaller number. Hopefully that logic makes sense, and b is the bigger number. When we do this, whenever we're working with greater than and equals to or less than and equal to, or equal to, that means that if you're going to graph it, the book likes to use dots, so you fill that in. Sometimes people have used on the graphs the interval notation, so then they have the bracket at A and the bracket at B, and when they're actually doing the plot on the number line. That is quite acceptable. A lot of students are more familiar with that, and that's quite okay. The book uses filled in dots and open dots to represent the same kind of thing. But if you're used to the brackets and the parentheses, you're welcome to use that as well. It is understood everywhere, generally. The interval notation, whenever the book refers to interval notation, it's going to use that bracket A, comma, B, and close bracket. That means it's all values between A and B, including A and B, hence the less than or equal to sign. For the second one, you just simply have the A is less than X, which is less than B. So the book will use the open dots to represent that it does not include the point at A, but it does all the other, also at B, but it does include all the values in between those two. What you're probably accustomed to seeing is the parenthesis there at A and the parenthesis at B with a line in between or filled in between. And the interval notation for that is again just using parentheses. From A to B, the parenthesis instead of the bracket means it does not include A, and it also does not include B. You can use any combination of the two. The third one means it's going to start at A, including A, and go up to B but not include B. Hence the close bracket with the A and the parenthesis at B. The fourth one, where A is less than X and also less than or equal to B, then again the open dot and the closed dot, or the parenthesis and the bracket with things filled in between. The interval notation of parenthesis A, comma, B, bracket means it's from A to B, including B, but it does not include A. If X is simply, or if A is less than or equal to X, the next line, well, it's going to start at A and include A and be every value greater than that. And in interval notation, you can see that you have the bracket with the A, meaning it's including A, on through infinity. And the next one, where A is simply less than X, but not equal to X, you see the change in using the parenthesis instead of the bracket. So that would mean it does not start at A, it does not include A, but includes everything greater than A up through infinity. Now, when it goes the other way, when the X is less than or equal to B, then it's going to be including, the graph will be including B and everything less than B. Hence the filled in dot under the geometric description that the book uses, and the interval notation has it set up. Now, whenever we do this, in interval notation, we're always starting with the lower value. Since it includes everything below B, we say that it starts at negative infinity and goes up to B. Now, you'll notice every time we use the infinity, whether it's infinity or negative infinity, you always use the parenthesis instead of the bracket, because we cannot say that it includes negative infinity because that's not an actual number. It just means that it goes down through negative infinity. That's a little point, but it's kind of picky in math. People expect to see that, and quite frankly, if they see a bracket with infinity on the interval notation, they get a feeling you don't really understand what you're doing. So it's good to at least appear that you know what you're doing. So then the last one, where x is less than or equal to b, it's all the values up to but not including b. And so you have the parenthesis on both sides, negative infinity up through b. The closing parenthesis instead of a bracket means it's going to be up to b but not include b. In working with some of the English of this, whenever problems talk about that x is at least, when you see this sign, it means it's greater than or equal to. X is at least 12, it means it could be 12, but it's also going to be greater than 12. So at least will mean that it's greater than or equal to. Another example, x is at least 5 means that x is going to be greater than or equal to 5. Again, at least means it could be 5, but it's also greater. It could be more than that. No more than means less than or equal to. X is no more than 20. It means it could be 20 because 20 is not more than 20, but it could be 19 or 18 or 1/2. So you see this kind of thing. No more than means it goes up to that number and stops. Up to also means the same thing as no more than, greater than or equal to. X could be up to 100, means it could be 1, it could be 2, it could be 90, it could be 56. It could also be 100 because it could be up to 100, but it can't be over 100. So up to means less than or equal to. Looking at a function. This is the book definition of a function. And if you start to read it, you realize that, oh boy, that's just a horrible definition of a function. One of the things that I like to do is to make it just a little bit easier to understand. So, simply put, a function is an equation for which any x can be put into the equation, and it will yield exactly 1y when you get the value out of the equation. So, you put in 1x, you get exactly 1y out. And when we look at this, the notation that we use, we're going to see it as f of x. And f of x is this f with parenthesis, x, close parenthesis. So whenever I mention f of x, that's what I mean. So sometimes this confuses people, or students, but simply think of it when you're used to seeing y is equal to x squared. Well, y is equal to f of x. So you might see things as f of x equals x squared. It's the same thing as y is equal to x squared. So don't let it throw you. It's just a symbol. So here's the function. F of x is equal to 2x minus 1. If you're given that, and then the problem asks you to find f of 3. Well, the 3 replaced the x. That means we put in a 3 every time we see an x in the equation. So again, if you're putting 3 in for x, you have to do it at all of the places. So an f of 3 would be 2 times what would be x you put in for 3, and subtract 1, and of course that's going to be 6 minus 1, which is 5. So it's not a hard thing, it just takes some getting used to, and the homework will help with that. Now, in the case where we have f of x equals 7, well, that means we need to set the equation equal to 7 and solve for x. Excuse me for that break in there. Gap between equal and 2, it's not supposed to be there, it just is. When f of x is equal to 7, that's like saying y is equal to 7. So you would simply set the equation equal to 7. So for example, f of 7, you would set 7 is equal to 2x minus 1, and then you use your algebra skills to solve, add 1 to both sides, you get 8 is equal to 2x, divide both sides by 2, and you get, of course, x is equal to 4. So it's not difficult, just something to become accustomed to using. Now, working with functions, we talk about domains and ranges. The domain is all of the possible values for x, the values that you could put into the equation. So if we look at this, what values could we put into this function? F of x is equal to f of x is equal to x squared minus 4. We say, well, couldn't I put anything into it? 0, 100, 1,000, -3, -3 million? Sure, you could. And you quickly realize if you think about it, that the domain is going to be all of the real numbers. Using the interval notation, you'd say it's a parenthesis from -infinity, comma, parenthesis, -infinity, comma, infinity, close parenthesis. And that would mean that it's all the values from -infinity to positive infinity. What are all the possible values of this function g of x is equal to 1 over x? Well, here we run into an exception. We realize, well, it could be 1, it could be 100, it could be 10 million. That works. And they could be negative numbers too. But the problem is, if x is equal to 0, we know we can't divide by 0. I like to joke that you can't divide by 0 because if you do that, your homework paper will just catch on fire. Well, while that may not be true, it is true that we can't divide by x. I can't divide by 0. So when x is equal to 0, that means we can't do that function. There's no real answer to that. So we would say that the domain, it's all of the numbers except 0. So we'd say it's all of the reals except 0. And if we wanted to use the interval notation, we would have the parenthesis -infinity to 0, close parenthesis, and also from 0 but not including 0 to positive infinity. So again, we want to be careful that we're using parenthesis in all of these. If we use a bracket, it would include 0, which we don't want to do. So one of the keys to this, whenever you're looking for a domain, check the denominator if you have a fraction, the bottom number. That can never be equal to 0. That will be a limit to the domain, and it will, whenever the whole denominator is equal to 0, it will not be in the domain. So you have to figure out what that is and say that's not in the domain. Now, working with square roots, what would be the domain of this function h of x? Now you notice I have kind of changed. I had f of x, g of x, h of x. It doesn't really matter what that letter is. It just simply means it's a function. So commonly we use f of x since it's a function, and we use f. But when we have more than one, we denote them differently. So h of x is different than any of the ones that we talked about before. Now back to the domain. With h of x is equal to the square root of x minus 1. Well, what would the domain be? Can we put in any number here? Can we put in 1? Yeah. Can we put in 1,000,000? Sure. Well, it's all the positive numbers. What if we put in 0? Well, we get the square root of -1. What if we put in any negative number, say minus 10? Well, that's going to be the square root of -10 minus 1, which is -11. Can we take the square root of -11? Well, if you've had some math courses, you'll say, well, you can always use the imaginary numbers, where I is equal to the square root of -1. But in business calculus, we're not dealing with imaginary and complex numbers. We're sticking with the reals. So we'd say, well, when the radicand, what is inside the square root, is negative, we can't get a real answer for this, a real number answer. So then they would not be part of the domain because we don't get a real number for the answer. So we're going to say, well, if that's the case, it is all of the reals that would be greater than or equal to 1. It works with 1 because 1 minus 1 is 0, and the square root of 0 is 0, but it can't be anything less than that. So we would say that it includes, in interval notation, we'd use the bracket to say that it includes 1, and then go to the positive infinity. So whenever you see square roots, just remember that with the domain, what's inside of it, the radicand, has to be 0 or greater. It cannot be negative at all. Wherever it's negative, that will not be in the domain. So just list where it's either 0 or positive, and that will be your domain. The range, if you think of the domain as all possible x values, the range is all possible y values, or values for f of x. So the range of this function, oftentimes what we have to do is look at this and say, well, are there any limitations in here? And what is going to be part of the range and what's not going to be part of the range? Well, if we put in all positive numbers, we're going to get, say, 1 squared is 1, minus 4 is negative 3. If we do 2, well, that's going to be 2 squared, which is 4, minus 4 is 0. If we do 2.5, 3, 3.5, 4, any real numbers in there. Well, when x is above 2, we're going to get a value of 0 at 2, and when it's above 2, it's going to continue to be positive. And we know, so it's going to be all of the positive numbers. When we put in 0, it goes down to negative 4. So we know it's going to include negative 4 up through all of the positive numbers. But since it's squared, we have to think about it a little bit. If I put a negative number, squaring it means it's a negative times a negative, which is a positive. So is it possible to get any value for f of x less than negative 4? If we try and put in negative 1, we get negative 1 squared, which is 1, minus 4 is negative 3. And if we keep putting in smaller and smaller negative numbers, more and more negative, well, then again, we're going to eventually end up getting positive numbers again because of the x squared. So we realize that the range of this, it's going to be all the reals that are greater than or equal to negative 4. It's not going to be, this function will not have any answers, or the range will never be below negative 4. It can include negative 4 when x is equal to 0, but it will never include anything less than negative 4. So the range is sometimes harder to figure out. You have to look at the problem and figure out what will my answers be. And that's a little bit harder than calculating the domain. Now, working with functions, there's also something called the range. And the range is simply all possible values for f of x, or just think about it as the answers that you get when you put in a value for x. Some students like to think of it as just the range is equal to all the y values. So, what's the range, excuse me, of g of a wait, g of a, not g of x? Well, just like we had f of x, g of x, and h of x, this represents a function in terms of x. G of a is going to represent a function in terms of a instead of x. So it's really the same thing. You put in a value for a and wherever the a appears, just like you did for x. So it's the same thing. Don't let it throw you. So what is the range of this function? 1 over a minus 4. Well, we notice that it's a fraction, right? 1 over something. Can this ever be equal to 0? Well, since there's a 1 in the denominator, if there's ever a number in the denominator and nothing else, that it just can't change, it cannot change, some kind of constant number, 1, 10, 15, minus 5, whatever it is. If the numerator can never be 0, well, if we think about it, then you can never get 0 as an answer. So from this one, we can look at it and say, well, 0 is not going to be part of the range. Well, what about other values? Well, let's look at positive ones. What if a was, say, 5? If a was 5, we would get 1 over 5 minus 4. Well, 5 minus 4 is 1, so that's 1 over 1, which is simply 1. So we know we can get 1. What happens if we make a larger? 1 over, say a was 6. 1 over 6 minus 4. 6 minus 4 is 2. So it's 1 over 2, which is 1/2. If a was 10, 1 over 10 minus 4 is 6. So 1 over 6 is 1/6. If a was 100, 1 over 100 minus 4 is 96, so it's 1 over 96. Well, we're getting all fractions there, and they're less than 1. What if A was 1,000,004? Well, that's 1 over 1,000,004 minus 4, which is 1 over 1,000,000. A very small fraction, but still a fraction. It's never going to get down to 0 because it can't, because of the 1 that's on top. Well, so we have positive fractions from 0 to 1, not including 0, but including 1. What about negatives? Well, we put in a smaller number, say A is equal to 2, we get 1 over 2 minus 4. Well, that's minus 2. So 1 over negative 2 is negative 1/2. And if we keep getting smaller values, when A is 0, it's going to be 1 over 0 minus 4, which is 1 over 4, negative 4, negative 1/4. So we're getting negative fractions. And as we keep getting more and more negative, if A was minus 10, 1 over minus 10 minus 4, well, minus 10 minus 4 is minus 14. So 1 over negative 14 is negative 1/14. Well, that's getting smaller and smaller, but it's negative. So again, if A was minus, let's say 999,996 minus 4 would be 1 over negative 1,000,000. Well, that's negative 1,000,000, or 1/1,000,000th. And so that's a very small fraction, but it's never going to get to 0. So we know that it goes between negative 1 and does not include 0. Well, what about if we didn't use any fractions there? Could we get a value greater than 2 if we use fractions? Well, let's see. If A was 4.5, 4.5, well, 1 over 4.5 minus 4 is 1 over 0.5. Well, 1 divided by 0.5 is the same thing as 1 divided by 1/2. And the 1 can be written as 1 over 1, and we're dividing it by 1/2. Whenever we have a fraction and we divide by another fraction, we invert and multiply. We take the denominator, flip it over, and multiply. So 1 over 1 divided by 1/2 would be the same thing as 1 over 1 times 2 over 1. Well, if you think about that, the answer is going to be 2. So as if we begin to use more and more fractions, say we used 4.9. Well, 4.9 in the denominator divided by minus 4 is going to be 0.9, or 9/10. Well, 1 divided by 9/10 is going to be the same thing as 1 over 1 times 10 over 9. That's going to give us something greater than 1. And as we keep working with this, we realize that we are going to get numbers greater than 1. And it can be all of them if we pick the correct fraction or decimal to do this. If we can do it with the positives, we can do the same thing, so that the denominator would be like negative 1/2 instead of positive 1/2. So it can include numbers greater than 1 and also less than negative 1. So whenever we see a fraction like that, for the range, the important thing is, remember, we can't get 0 as an answer because of the 1 on top. So the range for this is going to be all of the reals except 0, from negative infinity to 0 and 0 to positive infinity. It does not include 0. The second line is just a more mathematical way to write it. Is that you have the U, just think of it as the union, or and. You're putting things together. If we look at a graph of this function, we realize, yes, if we look at the y values, all as the x starts, this doesn't show the negative, but it would not include 0. It gets very, very close to 0 on the y values, but it does not ever touch a y value of 0, the horizontal value, or the vertical value of 0. So, but it can include all kinds of larger numbers. And sometimes students look at this and say, well, but the denominator can never equal 0. Again, that's when we're working with the domain, not the range. In the range, that just simply tells us that something strange is happening. And if we look at it, as x approaches 4, it goes from 0 to 4, the value goes down to like negative infinity. And then when you start at 4, it goes from positive infinity and comes down. So something strange is happening there. It's called an asymptote, which we'll get into later. But the values, the y values, all exist except for 0. Now, what's the range of this going to be? Well, we kind of have a clue from our working with the domain. If we have h of b is equal to the square root of b minus 1, we know that when working with square roots, the radicand, what's inside, can never be negative. That's going to limit our square roots, our answers, to be only positive numbers or 0. So 0 and positive numbers. So whenever we see a square root, we have to remember that and say that, well, the answer is never going to be a negative number. So it's going to be 0 and all of the positive real numbers, or from, as the interval notation there, the bracket 0 to positive infinity. Now, one of the things that sometimes confuses students is they have a function here and they say, well, I can do f of 3, but what if the book tells me to do f of a? Well, it doesn't matter. Whatever value you put in for x is what you put in every place you see an x. So an f of a is going to be 4 minus a over a squared plus 3. That's the answer. You're just simply plugging it in. It's kind of strange, but it's building towards using compositions of functions that we're going to do. So if you see this, don't let it throw you. Just put in the a value in for any x you see. We don't know what it is yet, but that's not important. The answer is simply in terms of a. Now, what if we did the same function, but wanted to find out what f of a plus 1 is? Remember, when we do this, an f of a plus 1, every place there's an x, we have to put in a plus 1. So I recommend when it's more than just a, put in parentheses, because on the top, the numerator, it becomes 4 minus the quantity a plus 1. If you put it in as 4 minus a plus 1, you're going to think of it as just that, and you're going to add 1 to 4. But in reality, because of the minus sign, you're going to end up subtracting. What do I mean by that? Well, when you take 4, it's minus a. It's like minus 1 times a plus 1. So you have to distribute the negative sign to everything inside the parenthesis. So it becomes 4 minus a minus 1, which then, of course, 4 minus 1 is 3, so you get 3 minus a. On the denominator, you have to square a plus 1. It's not a squared plus 1 squared, it's a plus 1 squared. That gives us a squared plus 2a plus 1, and then we still have the plus 3 that happens before. Now, everything's distributed, so we can add the 1 and the 3 together. So the final, or in the denominator, the final denominator is a squared plus 2a plus 4. And on the top, well, you can see the answer there yourself. So keep that in mind. If you're ever doing this, put the parentheses there to make sure that if you have to distribute a negative number, a negative sign or something, that you do it correctly. Now, working with graphing a line, the book uses the general form of a line being cx plus dy equals e. Well, that's what the book likes to use. Pretty commonly, you see it as the general formula for a line being ax plus by equals c. So if you're used to using that, go right ahead. It doesn't matter. But it's just this general form. And it's the linear function, which means it's going to be a straight line. Linear means line, so it's a straight line. Now, if we were working with y is equal to 3x plus 2, there's different ways that we can do this. One way is to plot points. You can go in and say that x is equal to 1. So when x is equal to 1, you would get 3 times 1 plus 2. That's 3 plus 2, which is 5. And do this for a whole bunch of points, and then draw a straight line between these points. The point form can be used. That if you can plot 2 points on it, then you can draw a straight line, or you could use this point-point formula, but there's an easier one. The point slope uses the slope of the line. The slope is the slant of the line, how much it goes up and down, and how fast it goes up and down. There's also the slope-intercept form. That looks at that same slope, but instead of using a point to graph it, looks at where it crosses the y-axis. And there's many different ways to do that. I'm going to focus on the slope-intercept form because it's a very easy thing to do. With a little bit of understanding of what slope is, you can quickly graph any line with very little difficulty. The slope of the line, as I mentioned, is kind of how steep the line is. And can also be thought of as the incline of the line, how much it's inclined. The book and in many different places refer to it with the letter M. You don't have to, but the book does. And the formula for slope is this m is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1. When you're doing this, it simply means you're looking at two different points. A set would have, one point would have x sub 1 and a y sub 1. The second point would be y sub x sub 2 and y sub 2. And for example, if we had this particular graph, we could pick 2 points on here, and I recommend finding a place, the points where they actually cross the x and y at the same time to make it nice and easy, like that point there and this point here. You can see it crosses at even values, so you're not guessing it. We know that that is at the first one is at 0.49 because it falls exactly on that, and the second one is at 0.2. You could use the other points, but you're kind of guessing where it would be. If you use the value of x was equal to 1, well, okay, so is that the y value when x is equal to 1? Is that going to be 3.5? Is it 3.6? Is it 3.75? Well, if you use it where it crosses an x and a y very evenly, it makes it a lot easier. So now we have our 2 points. Think of it as x sub 1 and x sub 2, or x sub 1, x sub y sub 1, and x sub 2 and y sub 2. So the subscripts just mean 2 different points. So we chose the 4,9 as the point at 4,9 as our first point, so let that be the x and y sub 1. So now the y value of that first point at 4,9 is 9, so we put that in for y sub 1, and the x value was 4 for the x sub 1 value, so we put that in, 4 in for x sub 1. Now we use our second point, and we take the 2 and the 0 and plug those in there as well. So the y value for the second point was 2, and the x value for the second point was 0, so we plug those values in. Now we just simply do the math. 2 minus 9 is minus 7, 0 minus 4 is minus 4, so the negatives, when you divide it, they cancel each other out, so to speak. Negative divided by negative is positive, so the slope is 7 over 4. So that's just simply a way of describing how steep the line is. It's just a reference point. It's a value. As you use it, it begins to make more and more sense. We could use a third point as we wish and check it, but when we do that, the slope value will be the same as the first section because the slope of a linear line is always the same any point on the line. If we use this point, it looks like it went down a little bit funny. It's at minus 4, minus 5. We look at it and look at slope as the change in y over the change in x. How much change in the y values happens over how much change in the x values. And when we're working with this, a positive line indicates the line is going upwards. If we work with this, the change in the value, going back to this change in y, the delta y, the changes in the x, or let's start with the change in the y. Well, the y value here was 2, and up here it was 9. So we did the 2 minus 9. But we can just simply count that and say, well, it's going from 1, 2, 3, 4, 5, 6, 7. It's going from 2 to 9. That's gone up 7. And we notice that that's this top number here as well. The change in x is it goes, from there we could say it's going over 1, 2, 3, 4. Well, we kind of noticed that puts us right on that point, and that the 4 is this number down here in the denominator. So the change in x, it goes from 0 to 4. That's the change. So the change in x. So whenever you see this kind of thing, a quick shortcut is simply to find a point, find a second point. See how the change in y is. It went up 7 here and went across 4. So it becomes 7 over 4. The change in y was 7. The change in x was 4. It works from down here too. We say, well, here we're going to go up 1, 2, 3, 4, 5, 6, 7 to get up, have the y value be the same. And then we're going to come over 1, 2, 3, 4. So again, the slope should be the same anywhere along the line. And the change from this point to this point in the y's was about coming up 7 and then over 4. So in working with slope, this can be a quick way to look at it. If you have 2 points, you can quickly calculate it just by counting how much you go up and how much you go over. That's going to be the slope. A positive slope indicates the line is going upwards, like this one, and a negative slope means that the line is going to be going downwards, like this line. So as we read slope, it's always from left to right, just like we read in a book. The blue line, it goes upwards from left to right. The red line goes downwards. Upwards is positive, downwards is negative. Now, this is the same line that we've been working with, and we note that the y-intercept is at 0, 2, as in that's where the y-intercept means that's where it crosses the y-axis. The equation of this particular line is 7x plus 8 minus 4y equals 0. Well, what would happen if we solved for y in this case? Well, we would subtract 4y from both sides. I just switch sides to make it a little bit more like we're used to seeing. Have the y come first, and then the equal sign and the x's and constants. And now we would divide each of these terms by 4. So we would get y is equal to 7x over 4 plus 8 over 4, which of course means that y is equal to 7/4 x plus 2. Now, what do we notice about this? Well, specifically, the plus 2 at the end of the equation. That's the same number that appears for the x. Pick your pen. This x 7/4 plus x plus 2. The plus 2 is the same thing as the y value, which marks the y-intercept. Where on this y-axis does the line cross? Well, that crosses here where x is equal to 2. So we notice that is the same. Now, the 7/4, well, that was the slope that we had up here. And again, we calculate the same way. From here, we can go up 1, 2, 3, 4, 5, 6, 7, and over 1, 2, 3, 4. Yeah, that's the slope. So we notice that this 7/4 is the slope of the equation. It matches what's up here. Now, if this is the case, you can understand why we might call this the slope-intercept form. This appears y equals 7 over 4x. The 7 over 4 is the slope. So whatever constant or value comes before the x is the slope, and whatever comes after that and by itself, a constant, just a number, the plus 2, that's where it crosses the y-intercept. Well, we can work with this to create lines easily, and also if we see a line, we can quickly come up with the equation of the line without having to go through a lot of work or be told what it is and figure it out. So this is referred to the slope-intercept form because it's using these two things. The intercept refers to the y-intercept, which is where the line crosses the x-axis, and our formula for the previous line was y is equal to 7 over 4x plus 2. So the generic form for this, the slope-intercept form, is y equals mx plus b, where m is the slope and b is the y-intercept. So again, this becomes a simple way that if we can get an equation into this form, we can quickly graph it because we know what the slope is and the y-intercept. Starting with the y-intercept, we plot that point, and then we can, from that y-intercept, use the slope to plot another point or another 2 points, and then draw a line. That's a quick way to do it. We don't have to use other forms which can be slower. Now, I don't require that you use this form in class. If you want to plot points, that's fine, but it just takes a lot more time, and this simply saves time. It's a good way to do it. It's nice and simple. Now, here's another line, and we notice that it crosses the y-axis at 0, -1. So the y-intercept is going to be -1. It's just whatever the y value is. And there's a second point down there. Simply picking that point because it crosses an x and a y at, it comes together at an x and y that's just very easy to work with. At 5, -7, you have this other point. You don't have to guess, it's just there. Using the slope-intercept form, we can quickly determine what the equation of this line is just by looking at this and using this information. It's going to be y is equal to the slope times x plus the y-intercept. Well, we already know that the slope intercept is at -1. So it's going to be plus a -1, which is -1. Now, to calculate the slope, I gave you the answer there already. But in working with this, to go from this point to this point, how much do we come down? Since the line is going down from left to right, we know it's going to be negative. Another way to look at this is saying, well, I'm going down with my y values, so I'm subtracting or reducing, going down with my y values, but then I'm going to go positive with the x value, and a negative divided by a positive is a negative. So from this point down to this point, how much does the y value change? Well, we come in and say, well, it goes up 1, 2, 3, 4, 5, 6 to here. So the y value goes down 6, hence the -6, and the x value increases by 5. 1, 2, 3, 4, 5. So hence we get the -6 over 5, which is -6 over 5. So we quickly, just by looking at this, knowing the slope and the y-intercept, we can use this slope-intercept form to quickly come up with the equation of the line. And it's really simple, really easy to do. Now, graphing using the slope-intercept form, if we start with this equation, well, the first step is always to solve it for y. So by subtracting 4y from both sides, we get 4y is equal to -12x plus 16. Divide all the terms by 4, and we get y is equal to -3x plus 4. Now, while the equation was more difficult to start with by solving for x. It's in a familiar form. It's already in the slope-intercept form. So we know that the y-intercept is at 4, and the slope is minus 3 over 1. So don't let that throw you. Just remember that the number here, if it's a whole number, it's simply 3 over 1. Now the y-intercept is at 4, so that means it's positive. So it means it comes up here 1, 2, 3, 4, and we know that it's going to cross here at this point. Our slope is negative, so we know it's going to go down. Negative 3 over 1, so it's going to come down 3, 1, 2, 3, and over 1. And we put another point here. That's 3 down from where we started and 1 to the right. If we wanted to go the other way, well, then we're saying, okay, we're going to go up 3. For it to be negative, if the y increased, it's positive, so we need to go negative on the x over to here. Now we have 3 points. 2 is all you really need for a line, but it does help it to be a little bit more accurate. And since this one is so easy, we can simply go up another 3 and over 1, put a point there, come down to 3 and over 1, and we can even do another 3 and over 1, so we can line it up easier. Now with the computer, I'm going to have trouble drawing a straight line, but it doesn't have to be perfect, as I'm sure when you do your homework, it won't be perfect, but if you have a ruler, it just makes it easy. So now you just simply connect the points. Like I said, it's not going to be real straight, but it's kind of close. So you get the idea that the line is going to kind of come down through here. And while it's not very neat because of using a mouse instead of a ruler, you get the idea. So it's a quick way to graph an equation, solve it for y, use the slope and the y-intercept to graph it. It becomes real simple. The last thing we're going to go over for the first day's lesson is a vertical line test. The vertical line test answers the question, is it a function or not? Earlier we defined a function as you put in 1x, you get only 1 y. Well, that is a function. So for every x, there's 1 y. If for any x, there are 2 y values, then it's not a function. So when we're working with this, that's the important thing to remember. Does every x have only 1 y? One way to test this is the vertical line test. To simply draw a vertical line anywhere on the graph and pick a point where it's determined, or draw several of them. But with this function, if we draw a vertical line anywhere, oops, that's not quite straight, but you get the idea. Anywhere that we draw a vertical line here, it is going to cross the graph only 1 time. So the vertical lines represent an x value, and it crosses just at 1 point for each of these, anywhere that we do this. So if we can do this, draw a vertical line, and it only crosses the original function 1 time for each line, then it's going to be a function. So to answer this, does every x have only 1 y? Yes, every x has 1 y, not 2. So it's a function. Now this one, we look at it and say, oh, well, hopefully this makes sense that this is not going to be a function, because anywhere that we draw a line where the function exists, we draw a vertical line. This line crosses the original line at 2 places. Since it crosses at 2 places, it is not going to be a function. The top one, the original function up for the first example, every time it crossed just once, so it is a function. Here, when we draw it, even if it happens only at 1 place, if you get 2 y's when you draw this vertical line for any place, then it's not a function. Pick a point that's wise, because you could say, well, I'll pick this point here, and there's only 1. I just kind of missed it there. Get a little bit closer. There's only 1 place that it crosses, right at that vertex kind of thing. Well, that's not a good place to pick it. You look at this, you can say, well, anywhere else that's less than that, any place you cross it, it crosses at 2. So this one is not going to be a function. It's a simple test, but it's a quick way to tell it. Just by looking at a graph, you know if it's actually a function or not a function. So, are these a function or not? For the first graph, for A, is that going to be a function? Well, yeah, we look at it and say, anywhere that we draw a line, we get it crosses the original equation only at one point. So A would be a function. So do you think B is a function? Well, hopefully you looked at it and said, well, they have a line drawn there already where it crosses 3 times. And you can draw other lines and it will cross 3 times. So since it crosses more than one time, it's not a function. What about the third one? Is that one going to be a function or not? Well, if we draw a line over here, crosses once. If we draw a line up here, crosses once. Well, all of these, when we draw one line, it only crosses one time for each line. So it appears to be a function, right? So well, what about at the y-axis? Well, this kind of graph, when it gets close but they kind of stop, it means it doesn't actually touch the y-axis. This one will actually be a function because every place that you draw it, what happens is that this line where the y-axis is, it's an asymptote. It gets very, very close. They say infinitely close. It gets really, really close to it, but it doesn't actually touch that line from either side. So there's this little gap at the y-axis where the line doesn't exist. That's okay. Whenever you have an x, you have it crosses once. At that x asymptote, that point is not defined, but it is still a function. So this one is indeed also a function. In this kind of situation, we see an asymptote, which we'll talk a little bit more about in the order in the class later. Now, the homework is a little bit different today. For the first day, I am asking you to review chapter 0. Strange to have a chapter 0, but it's like pre-algebra, stuff that you need to make sure you know before you start the actual calculus. So I guess you could call it pre-calculus. And look at the first 2 sections. We did review some of that stuff in this video, but make sure that it kind of makes sense to you. And sections 1 and 2. So when you look at the chapter 0, it'll say 0.1, that's section 1 of chapter 0, and 0.2 is section 2 of chapter 0. I have a graphing transformations video on Moodle as well. So look at that. It just gives tips on how to draw graphs or how certain graphs look so you can recognize them faster and easier. The number systems and basic terminology is a presentation that's also out there just to help you with some of the English if you're not familiar with it. The rest of the homework, I'm interested in that you understand the first 12 questions of section 0.1, and I would actually like you to do in section 0.1 numbers 13 through 25, just the odds. You don't have to do the evens. The odds would be 13, 15, 17, 19. The evens you do not have to do. That'd be like 12, 14, 16, 18, and so on. For numbers 27 through 46, do all of them, and then questions 53, 55, and 57. For section 0.2, do the first 11, just the odds, not the evens, not 2, 4, 6, and so on. And then 15, 17, 19, and 20. Now, I'll list these on Moodle, so you don't have to come in here to get them. And as I make videos, I may very well put these on, but I'm assuming you'll get it from Moodle as well. So you can go ahead and get started on that and have more tomorrow.